What if I told you that the strongest material on Earth is literally invisible to the naked eye? Welcome to today's explainer, where we're going to see how everyday carbon, yeah, the exact same stuff sitting in the charcoal of your barbecue grill, transforms into something with actual, literal superpowers when we shrink it down. We are zooming way in today, far beyond what any standard microscope can even pick up, right down to the arrangement of individual atoms, to uncover how making microscopic tweaks is creating the materials of our future. Here's our roadmap for today's nano zoom. 1. Enter the nanoscale world. 2. Fullerenes, hollow carbon cages. 3. Carbon nanotubes, mighty cylinders. 4. Graphene, the 2D wonder. 5. Real-world nanotech applications. And 6. Future risks and rewards. All right, let's kick things off with part 1, Enter the nanoscale world. So when we talk about a nanoparticle, we're talking about something ridiculously tiny, a particle with a diameter between just 1 and 100 nanometers. To put that completely mind-bending measurement into perspective, 1 nanometer is a billionth of a meter. We are talking about structures built from just a handful of atoms. At this scale, the normal rules of bulk materials just get tossed out the window, and that's exactly what gives these particles their unique properties. Think about a standard chunky block of carbon for a second. Most of its atoms are safely hidden away on the inside, meaning they can't really do anything, they can't react. But a carbon nanoparticle? It is so incredibly tiny that a massive proportion of its atoms are fully exposed on the outside surface. Because it has this huge surface area to volume ratio, way more atoms are available to interact. This means we can use much smaller quantities of nanoparticles to trigger significantly faster, more effective chemical reactions than we ever could with a big block of the exact same material. Moving on to part 2, fullerenes, are hollow carbon cages. You'll want to lock this specific number in your brain, 60. This represents C60, the most famous fullerene out there, affectionately known as Buckminster fullerene. It's a molecular form of carbon built entirely out of atoms arranged into a hollow shape. If we zoom in on the chemistry here, it is a microscopic masterpiece. Crafted from exactly 12 pentagons and 20 hexagons, every single carbon atom forms strong covalent bonds with 3 others to build a perfectly symmetrical, hollow cage that honestly looks exactly like a nanoscale soccer ball. But here is where things get really interesting. Inside that molecule, those bonds are super strong, but between the separate fullerene molecules themselves, the intermolecular forces are actually incredibly weak. Because of this, fullerenes have surprisingly low melting points. You just have to overcome those weak forces to melt them down. Also, even though every carbon atom has a delocalized electron, those electrons get trapped and can't jump freely between the separate molecules. That makes fullerenes pretty poor at conducting electricity compared to their other carbon cousins. Let's shift gears to part 3, carbon nanotubes, the mighty cylinders. Imagine taking a microscopic sheet of chicken wire and seamlessly rolling it into a glowing tube. That is exactly what a carbon nanotube is. They're cylindrical structures made of carbon atoms arranged in repeating hexagonal rings. Geometrically speaking, you can just think of them as rolled up sheets of graphene. And these cylinders come in 2 primary flavors. You've got single-walled nanotubes, which are exactly what they sound like, a single rolled layer of carbon forming the tube. Then you have multi-walled nanotubes, which are basically microscopic Russian nesting dolls, featuring several concentric layers tucked inside each other. But both types share this incredibly efficient arrangement of atoms, with a ton of empty space right down the middle. Their stat sheet is just off the charts, thanks to those strong covalent bonds and an awesome hexagonal structure that distributes forces perfectly. Nanotubes have extremely high tensile strength. Yet, because of all that empty space inside the cylinder we just talked about, they have a very low density, making them impossibly lightweight. On top of that, the delocalized electrons can zip freely straight down the entire length of the tube, making them fantastic conductors of both electricity and heat. Which brings us to part 4, graphene, the 2D wonder. So graphene is essentially a single layer peeled straight off a chunk of everyday graphite. Seriously, the pencil sitting on your desk right now is made of millions of layers of graphene stacked on top of each other. When you isolate just one of those layers, you get a completely flat hexagonal lattice of carbon that is exactly 1 atom thick. It is a true, impossibly thin, 2-dimensional wonder. Because every single carbon atom in this flat lattice forms 3 strong covalent bonds, it is literally one of the strongest materials known to humanity. Yet, it has virtually no mass. The secret sauce? Every carbon atom tosses in one free-roaming electron that is completely free to zip across the entire flat surface. This means graphene manages to be flexible, bending easily without snapping, while being an absolute powerhouse for conducting electrical and thermal energy all at once. Now for part 5, real-world nanotech applications. Why does this actually matter to us? Well, when engineers need to select the right nanostructure for a job, it's a game of trade-offs. The hollow cages give you moderate strength but pretty poor conductivity, while the cylinders and the 2D layers just absolutely max out the charts in both categories. It creates the perfect menu for materials scientists. And by exploiting these unique properties, we are actively revolutionizing whole industries. We're using fullerenes as tiny hollow delivery vans to drop medicine directly into specific cells for targeted cancer treatments. Because of their insane strength-to-weight ratio, we're reinforcing bicycle frames, tennis rackets, and even aircraft parts with carbon nanotubes. Graphene is paving the way for rollable electronic screens, highly efficient batteries, and microscopic transistors. Plus, thanks to that massive surface area, all of these nanoparticles serve as incredibly efficient chemical catalysts, speeding up industrial reactions and lowering costs across the board. Let's hit pause for a quick mythbuster, though, because it is so easy to get the bonding rules mixed up at this scale. One of the most common mistakes people make is assuming that graphene, simply because it's so thin, is made of separate molecules just like fullerenes. The answer is a hard no. Unlike fullerenes, which are distinct, separate molecules with weak forces between them, graphene, along with graphite, is a giant covalent structure. This means it's a chemically continuous network of strong carbon-carbon bonds stretching out in every direction across that 2D layer. There are absolutely no individual molecules in graphene, just one massive connected lattice. Finally, let's look at part 6, future risks and rewards. The very thing that makes these particles so revolutionary, their microscopic size, is exactly what makes them a potential hazard. Careful testing is desperately needed right now. We honestly still don't fully understand their toxicity or the long-term effects on human health if they are accidentally inhaled or absorbed. Furthermore, if these nanoparticles leak into our water systems or soil, their tiny size makes them incredibly difficult, if not entirely impossible, to filter out or remove from the environment. Which leaves us with a critical, ongoing debate that scientists are grappling with today. Do the miraculous benefits, like targeted cancer cures and highly efficient energy storage, outweigh the microscopic, unknown risks to our environment and our health? Are we truly ready to fully embrace these carbon superpowers when we don't entirely know the consequences hiding at the nanoscale? Thanks for tuning into today's Explainer, and we'll see you next time.